So welcome back for the last session of the day and before the round table that we end the day also. So this session is about electronics and software for big data, and the first talk will be given by Antsa Randriamanantena on Prospective on electronics and signal processing R&D.
Good afternoon, everyone. My name is Antsa Randriamanantena, and I'm working at the Laboratoire of Data Physics de Bordeaux. So thank you for having me here today. So I'm giving this presentation on behalf of the electronics group from the lab. And I will talk about two different projects that we are conducting. And I will start to talk about ALMA, some electronics R&D that we are conducting for ALMA, and at the end of this presentation, I will give a quick overview of the electronics and the signal processing that we are doing for a new project, SPIAKID, that can be used for ELT, for example. So the lab and ALMA, the lab has contributed to the ALMA construction phase with a different subsystems that are presented here, from the digitizer to the tunable filter bank cards that are inside the correlator system. So the electronic groups from the lab is still involved in the ALMA project by the maintenance of the different subsystems that have been developed, and also for development studies that is supported by ISO since 2013. And we are designing solutions in relation with the ALMA development roadmap for the bandwidth improvement of the ALMA and also the sensitivity. So here I give some links for the report that have been delivered for the several development studies that we have been undertaken. So you can see these reports, and also an article that have been published in the ISO Messenger. So you can see here a small glance of what it looks like. So here is presented a scheme of the digital system that is proposed by a lab for the upgrade of the ALMA system. So our proposal starts from the digitizer part of the electronics till the first step of the correlation effect. So I will be more I will give more detail about that later. So here is the development project plan for the next years for our team. So our idea is to submit a new project for the ISO in the November 2021. So the main objective of this new project is to perform end-to-end system demonstration of the previously identified solution for the digitization of the signal, and also for the data transmission from the antenna to the correlator, and also digital signal processing for the signal pre-treatment. And the idea is to use off-the-shelf hardware when it is possible to do this system demonstration, in order to have a quick validation of the solution that we had in mind. And in parallel of this work, we will have a consolidation of the hardware design that will reach, we hope, a PDR level for pre-production in 2024. So the idea is to produce these subsystems and to integrate the new subsystems in the ALMA environment until 2026. Okay, so here I will give a quick recall of what looks like the ALMA architecture and the electronics that is inside ALMA. So at the antenna, we have the digitizer, some electronics that format the data before the transmission. And at the AOS building, we have also electronic board to receive the data. We have also the tunable filter bank card that split the wide bandwidth signal into some smaller bandwidth before the correlation. And we have the correlator electronics at the end of this chain. So the current digitizer is based on a 3-bit sampling digitizer that works up to 4 gigasamples per second. And the new architectures may look like this. So at the bottom of this slide, you can see a block diagram that describe what can be the new ALMA system. So what we propose is a new digitizer that works at 40 gigasamples per second. So this is 10 multiplied by 10 in frequency sampling. And we propose also to have the first step of digital signal processing at the antenna, and the second one at the OSF inside the correlator. So this digital signal processing was identified during our previous studies, and I will show you what it looks like later. So to give a little of detail concerning the digitization. So here is the module that we are propose now. It is a module, a digitizer module that is delivered by a German company, which is Micram. This module is a 2 interleaved cores ADC that run up to 40 gigasamples per second. At the beginning, the module was supposed to run only up to 34 gigasamples per second, but the company told us that it could be reached the 40 gigasamples per second performance, but they didn't have the facility and the equipment to test it at this rate. So we proposed to have a test campaign at our facility because we have the environment and the experience with this kind of FPGA environment. So we had this test campaign in our facility, and we performed the digitization up to 40 gigasamples per second. So this has been confirmed by Micram later, and here we show some curves with the performance at 40 gigasamples per second, and you can see that the effective number of bits and the performance in terms of bandwidth. So the effective number of bits is between 4 and 5 in the 0 to 20 gigahertz that is considered by ALMA, and also for the bandwidth, we have 20 gigahertz bandwidth with minus 3 dB cut-in frequency. So in order to have a real performance measurement of the Micram, we did some statistics and spectral analysis of the digitizer. We also improved our knowledge of the efficiency, the digitization efficiency of the device by using the signal-to-noise ratio measurement instead of the given effective number of bits that is given by the company. And this kind of measurement is, we think, fits better with the requirements that is given by the project, which is 99% of efficiency for a normal observation condition. So here you can see in the bottom right a curve of maximal efficiency measurement that we did in lab compared with some curves with a perfect ADC from 4 to 6 bit. So as you can see here, the efficiency of this digitizer can be compared in some frequencies with the efficiency of 5 bits, and in some other frequencies with 4-bit ones. So here is an example of the digital signal processing that we can do inside the antenna. So the idea is to split the original 2 to 18 gigahertz sample bandwidth into some pieces of 2 gigahertz band. So we do this within a parallel architecture inside the FPGA. So we have signals that is delivered at 40 gigasample per second, but the internal clock of our FPGA is around 300 megahertz. So we have parallel processing inside the FPGA. And for example, to implement this kind of frequency slicing, we use up to 3,000 real multipliers inside the FPGA. And this is an example of what it is done. So this is a polyphase filter bank with an oversampling factor that is not, so here the band from 0 to 20 is divided into 8 pieces with some overlapping of different bands. And this overlapping makes it possible to have a flat and contiguous responses of the Fourier transform after the correlation. And so here we have an input with 2 tones at different amplitude. And the idea is to compare this input with the 8 piece of smaller basebands. And here, as you can see, we have the 2 tones with a zoom in of 2 gigahertz bands. So for ALMA, we have at the digitizer side up to 100 of terabits per second data rate. And after the correlation, for sure, we have huge amount of data that can be compared to big data problems. So here I presented the different technology that could be used for processing. We can use ASIC that is used today for the current correlator system, but we can also use FPGA, GPU, CPU. The matrix that is in this diagram is the flexibility and ease of use of this technology compared to the performance and the power efficiency. And as you can see, the efficiency is the main advantage of FPGA and ASIC, but the flexibility of this kind of technologies are not sufficient. And we also have a lack of understanding and expertise of this kind of technologies by the common people. So today, the developers of such technologies, the funder and the company tend to propose tools that have different level of, let's say, understanding and usability, and can target different type of developers, from hardware developers to software, and also for data scientists. So FPGA is today evolving and targets a bigger and bigger people and public. So I'm going to talk a little bit about SPIA-KID now. So the MKIDS detector are recent technologies, and it is based on the superconducting LC resonator that have a resonant frequency that is modified by the photons that hit the detector. And with this kind of detector, we can identify the individual photons and measure their energy individually. And in the frame of this project that is funded by NERC, we are developing with collaboration with the GP, a concept of spectral imaging, exploiting this kind of detectors. And we are carrying the readout electronics development. So here is the number of, is given the number of pixels that is targeted for this SPIA-KID. So we try to implement a mosaic of detector that can reach up to 80,000 of pixels, and we will have 20,000 pixels per detector and 2,000 per line. So we'll have 10 lines per detector and 40 lines for the mosaics. And for each line, we have to use ADCs and DACs to read out these detectors. And after digitizers, we have to use, like in ALMA, FPGAs to identify the photon that hits the detector, and also to estimate the energy and time tag these events. So it can be very similar to the work that we do for ALMA and also for other projects like SKA. So that's why we have been asked by the GP to do this work. And also for this kind of project, we have a problematic of also of big data and the big data rate, because the flow of data is about 100 gigabit per second per readout lane. So here we have 40 readouts, so we can reach up to 4 terabit per second. And if we have a bigger number of pixels, let's say for example for application for ELT, the data rate will be huge, and this can be an HPC problem also. So our first idea to scale up this kind of technology is to have some data reduction software that is implemented inside the FPGA. So we are trying to find algorithm that can be implemented inside the FPGAs, and algorithm also that can ease and reduce the data volume that comes out of this kind of technology. So here I put some sketches and an example of what we can do. So at the bottom left of this slide, you can see a diagram of the signal chain that is presented in the thesis of Matthew Schrader from the University of California. And they proposed a scheme with coarse channelization, like in ALMA, and the fine channelization for each pixels. So this kind of techniques is very demanding in terms of resources inside the FPGA. So if we scale up this kind of architecture, we will need a lot of FPGAs. So we were trying to simplify this kind of channelization by using here neural networks to identify only and characterize only the pixel that has been hit by by a photon. So here we use a very simple neural network, which is an MLP, multi-layer perceptor, for detecting the photon that hits the pixels, and then reduce the data volume that come out of the FPGAs. So quick look at the performance of the neural network that we have initiated for this project. So here, the training is based on simulation data of the phenomenon of the superconducting and the MKIDS technology. So the very first idea that we have is to test that this kind of neural network can be used to reduce the data volume for SPI-KID. So the first result is very very interesting. We have a performance that is good for the requirements of the SPI-KID project, which is a detection of up to 99% of the photons and false negative and false positive of 1%. So this is very promising, but the difficulty is to use this kind of training for the real data and in the real environment. So the next step is to identify the calibration step and how we can use this in a real environment. Xilinx, like I said before, propose some tools that can be very user-friendly. So here you can see that libraries from Python and so on is available in a design flow that generate FPGA bit stream from a Python code of neural network. So that's why we have been able to develop in a very limited amount of time a neural network that can do big things. So this is very promising also. So the next step of this data reduction and imaging is to form images by integrating different events and also perform some images transformation, some correction of the atmospheric dispersions and so on. And these developments will impact the readout electronics and the calibration plan. And also we need to have some detailed model of the data in order to have new signal processing and image processing algorithm that can be implemented in a mixed architecture using FPGAs and also conventional CPU and GPU architecture. So that's why I put this final slide with the multiprocessor system on chip architecture. So today, FPGAs founders have this kind of SoC, system on chip, that integrate different processors, CPUs, GPUs, NPUs, and with FPGAs. So this makes it possible to have an adequation with algorithm architecture and to have a better efficiency, and also makes it possible to adapt different algorithms with the existing infrastructure. So I would say that it is sure that for the future, the processing is for will target heterogeneous architecture, and it was said before in the previous slide, in the previous talk, but I emphasize that this kind of architecture is the future of processing. So thank you. If you have any questions.
Yes, there is a question from Jérôme and Christophe. So Jérôme.
So for the ALMA backend, For the Yanma backend, what is are there source of spurious spikes? Are there source of spurious spikes in the scheme that you proposed, or not at all?
A source of spurious spikes?
Yes.
You mean because of the ADC architectures?
Yes.
Oh, okay. So this has been studied during our previous studies. We have performed measurement of interleaving spurious using this kind of architecture, and we made out we eliminate the spurious signals in a level that is lower the quantization noise. So I will say that with a particular calibration algorithm that we implemented, we don't have this kind of spurious forward.
Okay. And what would be the typical channel resolution to cover 20 gigahertz of bandwidth?
The channel resolution that you mean from the correlators?
Yes.
Yes. Okay. So now I don't know if you are aware of that, but there are different I would say projects of correlator, and one of them is proposing a normal mode with 200 kilohertz spectral resolution, and with zoom-in mode in different windows that can be 64 times lower than that, so we can reach up to 0.2 kilohertz. And
yeah. So, but it would be 200 kilohertz over 20 gigahertz.
Yes. Yes.
And there would be when you're going to higher resolutions. So when
yeah, you will
then
have smaller bandwidth.
Do you compromise the bandwidth?
Yes.
I mean, can you get at the same time the full bandwidth at 200 kilohertz and part of it at high spectral resolution?
I would say you have to trade. Okay. You have to make some trade-off between the full bandwidths, but what is very interesting that you can put some different windows inside the 20 gigahertz.
And any idea of the cost of this full correlator for ALMA?
Oh, I only aware of what would be the cost for our part, but for the correlator part, I can say.
Okay, thank you. There is a question from Christophe Rizachi. He's in the train, so he cannot talk, so I will ask it for him. So what about the linearity of the 0 to 20 gigahertz digitizer? Is it difficult to optimize, calibrate?
So I would say that at the first start, it was difficult to reach better linearity because we are not familiar with this kind of interleaved technology, and the ADC is interleaved and also interpolated one, so this makes it more complex to calibrate. But at the end of the day, we made out to reach some performance that is correct for ALMA. So the non-linearities have impacts on the efficiency, and that's why we tried to measure very accurately the efficiency of the digitizer. So having an efficiency of 99%, the non-linearity is not a problem at all.
Okay, thank you. Carl Schuster has a question.
Yeah, can you say a couple of things on what kind of interface is included in the micro chip?
In the micro chip?
In your ADC chip, what kind of, after the ADC, what kind of preparation for the data links is available?
So the microARM chip is very simple in terms of interface. It is a non-standard protocol, but it implements a PRBS, so it is a modulation of the signal that is coming from the ADC, and we can retrieve the signal by performing some demodulation in an FPGA. So after that step, we have to format the data inside an FPGA in order to be able to transmit the data. So we have to do some data preparation in an FPGA, not inside the ADC.
Okay, thanks.
Thank you very much.